kids, time for our last section. Now, it'll take us a couple lessons to get through section 2.6, but it deals with something we call exact differential equations, and it's going to involve some of the skills that we learned kind of in the maybe first quarter of multivariable. So first, the definition. The differential equation that looks like this, and of course I can manipulate this so I have dy dx is equal to something, but this is the form that you're going to be, that's going to be the easiest to work with when we're dealing with exact differential equations. So this differential equation is exact only if, I didn't misspell if, it's if and only if this statement is true. Now let's think about what that statement means. So m, right, I have some function m times dx. So it is a partial derivative with respect to x. So what this is saying is that if you now take the derivative of a derivative, but a partial derivative, with respect to the other variable, and you take another derivative of this function n, but with respect to the other variable x, if those two partial derivatives are equal, then we say that the differential equation is exact. And if the differential equation is exact, the solution is a function, potential function f, right? Parent function f, in terms of the two variables, equal to a constant. Do you see why the constant needs to be there? Right? Because the derivative, right? If I took the derivative to get here, the derivative on the right side was equal to 0. So what does that what does that mean? Right? It means this right side, this k had to be, there had to be a constant there. Take the derivative and get 0. So to the exact differential equation, this is what the solution looks like as long as you have an exact differential equation. Now think about, this is where multivariable comes in. Can you think about what that meant when we were in multivariable? What does that look like? Oh, I forgot. I wrote this. I can, of course, always check my solution. Anytime I go from a derivative to original, by the way, how do I get there? Integrate, right? How can I check my solution? Differentiate. And if you differentiate and you take the partial of this function with respect to x, you should get m. And the partial of this function f with respect to y, and you should get n. So again, let's talk about what this looks like. Some function with the domain in the xy plane is equal to a constant. Do you remember what we called that? A level curve. Here's an example of a level curve from multivariable. Right? I told you that maybe we had this function that gave us this, right, this conical shape thing. But if we said the function was equal to a constant, it was like all these slices, right? K equals 1, k equals 2, k equals 3. And if we look down upon, right, from the bird's eye view, right, from the z, we would see all our level curves here on the xy plane, right? Remember that? Here's another example of a, but this example we're actually going to do. So I have some function f. It's, right, elliptical, but I'm saying it's equal to some constant c or k, whatever we want, right? So I have a function in terms of two variables equal to a constant. This is a level curve. I want to take the partial derivatives of f, and here's what I get, right? I took the partial of that function with respect to x. 4x minus, right, with respect to x, y is the constant. So what is the derivative of a function times a constant? Well, it's just the constant. And then, of course, 3y squared goes away. What happens when you take the partial of f with respect to y? Right? This term goes away because it's only in terms of x. You get negative x, right? Because now you're taking the derivative with respect to y. So what is the derivative of a constant times a function, well, it is the constant, negative x, and then of course plus 6y. I'm going to call that m and this n. And then I'm going to check to see if I have an exact differential equation. Right? If I call this m the partial of f with respect to x, and I call this n the partial of f with respect to y, right? These, if you multiply this by dx, right? Right? That's what it looks like. But I am just going to look at each one of these and take the partial of m, which is already a partial derivative, but I'm going to take the partial of m with respect to the other variable y. So taking the derivative of this expression with respect to y, the x goes away and I just get -1, the coefficient in front of y. Then I'm going to take n, which is already a partial derivative, but I'm going to take it with respect to x. And the derivative with respect to x would also be -1, right? The constant in front of x. And then 6y is also a constant. So what is true about, right, f of, so what this is actually is f of, we did x and then y. This is f of y, but then x. Since those are equal, we have an exact differential equation. So in this step, I started with the original. I took the partials, and then I checked to see if it was exact. We're going to go backwards. I'm going to give you the differential equation. You're going to check to see if it's exact. If it's exact, you have to undo the derivatives, which means you're going to integrate to get back to the parent or the potential. Okay, so that's our goal. That's what we're going to do. So let's go. Oh, I forgot my little note. Therefore, the level curve f is continuous and differentiable on the domain region. So, I mean, that's like a fine print thing, that going backwards from a differential equation and going to the potential, you want to know that, okay, I don't have any issues anywhere, right? I don't have to solve for my domain interval or anything like that. I just need to know if I can do this exact differential equations, I can verify this. I do know that my level curve f was continuous and differentiable. All right. So first, I just want to do some practice verifying that we have exact equation or not. So I just want to know if the partial of what we call m with respect to the other variable is equal to the partial of what we call n with respect to its other variable. So here's 4 equations. You might want to stop the video and do this yourself. But for each one, you want to figure out who m and n is. So remember, this is already a derivative with respect to x. This is already a derivative with respect to y. So all I need to figure out here is the partial of m with respect to the other variable equal right? So hopefully this isn't too hard. Thank goodness we did practice partial derivatives in, right, multivariable. So that's just 2x with respect to nx is also 2x because the y's go away. They are equal, therefore, yes, this is an exact differential equation, which means I can use the method of going backwards to find the solution. How about this one? So this is not a product rule, right? Because I'm taking the derivative with partial derivative with respect to y. So x is just a constant. So e to the stuff times the constant x, right? A constant times e to the stuff. Its derivative is the constant times e to the stuff times the derivative of the stuff with respect to y. So I have x squared, right? How about the next one? Now I'm taking the derivative with respect to x. So I'm taking the derivative of e to the stuff times its constant times the derivative with respect, hopefully you can already see this, right? Derivative with respect to x, which is going to be y. These two things are not equal, therefore no, not exact. And I'll leave it to you to show that the next one is not. Be careful. Look, I mixed this up. Be careful. This is n, and this is m, right? Just be careful that you're going to take the partial with respect to the other variable, right? These are not equal. This is not exact. And look at this one. Be careful with this too. Look, you're like, whoa, where's the dx, right? This is really dy dx. And you're just going to multiply everybody by dx. So you do end up with a dx here and just a dy here and still 0 here. So this is your m, this is your n. These will show up to be equal, and therefore, yes, this one is exact. Okay, so far we have 3 exact differential equations, right? The one that I just showed you in the previous slide, right? Where we ended, but that one I actually started with the parent function, got all the way through and showed you, yes, that you had an exact differential equation in the middle there in those middle steps. And then we have this one and this one, and we are eventually going to solve all 3 of those. Although, and you already know the solution to the first one. All right, so this is number 1 on this slide, right? Notice that the directions say solve the exact differential equation. See, hello, you have exact. You don't need to verify. Please read your directions. If I just say solve the differential equation and you want to try to do this method, you have to verify that you have an exact differential equation. I don't have to verify this. I mean, in reality, we just did on the first slide, on the previous slide. But if the directions tell you you have an exact differential equation, you do not need to verify it. So I'm going to identify my m and my n. And step 1 is to integrate. Pick one of them and integrate. It doesn't matter which one, but what you want to think to yourself is either m or n easier to integrate than the other one? And I would say in this case, no, it doesn't really matter. Therefore, I'm going to, just by default, I am used to integrating with respect to x. So I'm going to choose m to integrate. So remember, m is already a partial derivative. So I'm going to anti-differentiate m, which is the partial derivative of a potential function I don't know. F is who you're after. I don't know who it is. I'm trying to peel off the derivative. So I'm peeling off the partial derivative with respect to x first. So I'm integrating with respect to x, which means I'm going to integrate the right side with respect to x. And I've made y purple, so you remember you're integrating with respect to x, and the y doesn't match. So when I anti-differentiate this, the f drops out. Anti-differentiated here with respect to x, which means I got x squared over 2. That's just the constant multiple, right? The constant just stays there. And then integrated x to the first, which got me x squared over 2, right? This 2 canceled out with the 2 that was here. Plus, right? This is kind of sort of a plus c, but remember when you're doing partial derivatives, which is why I did that 2 slides ago. Remember, when you take a partial derivative with respect to x, any function in terms of y only, poof, disappears. So I have to remember when I'm anti-differentiating, I have to remember to put that back. And remember, our potential function was a level curve, right? So it is equal to k. When you take the derivative with respect to x, you will get 2xy plus x, and again, you'll be equal to 0. So I just need to get the g part. So how do I get the g? Well, remember, the g is a function in terms of y, but I have a partial of f with respect to y right there. So since I integrated with respect to x, I'm going to differentiate with respect to y. In this case, my other variable is y. So take a moment to look at that. So here is what I'm going to take the derivative of. That came from right here. I'm going to kind of ignore my k for a minute, right? Because it's just the derivative of that is going to equal 0. I'll put it back, but I just want to highlight the fact that what's going on here. Here's the expression I got for f. I want to take the derivative of it with respect to y. But remember, I already know what the partial of f with respect to y is. It's called n. I already know that. So when I took the partial derivative, which I got x squared, right, the coefficient on y, 1/2 x squared went away, and then g prime. When this expression is equal to n, but you know what n is. N is the partial of f with respect to y. You just figured out that n is equal to x squared plus g prime, but hello, you actually know what n is equal to. It's x squared plus y, because this is an exact differential equation. Canceling will always happen, and look at what I have left. G prime of y is equal to y. Can you tell me remember what I'm after at this point? At this point, I almost have my f. The only piece I'm missing is g of y. I'm almost done with the solution. My only goal was to get g of y, so I took the derivative so I could get g prime, because I already have g prime up here. Did canceling, which will always happen when you have an exact differential equation. Now I want to find g to be able to plug that in, so I'm just going to integrate again. Integrate g prime, but g prime was equal to just y, so there it is. Integrate y with respect to y, I get 1/2 y squared plus a constant, and I put a subscript of 1 there for a reason you'll see in a minute. So now I am just going to pull this whole equation, copy and paste down here, but I'm going to be able to fill in for g of y. Right? There it is. F in terms of x of y is x squared y plus 1/2 x squared plus, I found what g of y was, 1/2 y squared plus a constant, a pure constant, not in terms of any variables, is equal to k. But now how we generally write this, remember k was just a constant, right, of what z, right, of z height. So I'm just going to, right, if you want, subtract c1 from both sides, but a constant minus another constant is just a big old constant. So we usually represent the solution like that. Can you check your work? Sure. If you wanted to check your work, and I'll leave that for you to do, well, you take the partial of this with respect to x and take the partial with respect to y, and you know what you're going to get? M and N. That's what you're going to get. Hey, sounded like M&Ms. M and N. Woohoo! All right, let's try another one. So notice here, it just says solve the differential equation. It didn't say exact, gosh darn it. So if I identify M, oh, that's out of order. M and N, I want to see if this potential function that I'm looking for, that part is M, is the partial of M with respect to Y equal to this partial of N with respect to X. So let's take a look. Right? What is the partial of M with respect to Y? Hey, this kind of seems familiar. Have I done this already? That's called planning, kids. These two things are equal. Therefore, yes, this is an exact differential equation, and therefore I'm going to go that really was step one. So now on the previous slide, this was step one. I had to do a prequel step. I had to do a new step one on this one simply because they didn't tell me it was exact. Once I verified it exact, I'm going to do the same process. Now for this one, again, you can integrate either one. It doesn't matter. In this case, once again, both of them are easy to do. And I'm just going to demonstrate picking N this time, just to show you it can be done. So I take N, which is already a derivative, the partial of some function f I don't know. With respect to y, I'm going to anti-differentiate both sides with respect to y. And when I do that, I get f is equal to y squared over 2, which cancels out and makes this 3. Remember, x is the variable that is like a constant. So the antiderivative of a constant is that constant times y to the first over 1, and then plus some function in terms of x is equal to my k. Now I'm going to differentiate with respect to the other variable. I anti-differentiated with respect to y. Therefore, I'm going to differentiate with respect to x. So differentiate f, a function I can't see with respect to x, but I already know its partial derivative is m. I already know that. So I'm looking here, and I'm taking, remember that I'm going to get the derivative of is equal to 0, I know. Take the partial of this expression with respect to x. The y thing goes away. The partial with derivative with respect to x means you just have the constant negative y. And then the derivative of g of x is g prime of x. That's equal to m, but I already know what m is. Notice again, because I'm exact, what happens? The y's go away. So I have g prime of x is equal to 4x. Now I'm just going to integrate to find g, because remember, I'm almost done. Up here, f, I'm almost done. I have two of the three terms. I just need to solve for g. So I have g prime of x is equal to 4x. If I have g prime, how do I get g? Integrate. When I integrated g prime, I was integrating 4x with respect to x, which is 2x squared plus a constant. And if you want to just forget this constant here, right? And just know what you're doing, I'm fine if you skip that step. So I'm copying this f over, all of this over. My potential function f, my parent function f in terms of the two variable is I already found those two terms, 3y squared minus xy, but I now found 2x squared plus one constant. I'm a level curve, right? I'm equal to K. But remember, those two things are all going to wrap up into one. And, oops, copied over something wrong. That's not there. I just did some reordering to lead with x. 2x squared minus xy plus 3y squared is equal to c, because that is, if you go back 3 slides, right? I think it's 3 slides. I started with this, right? I said, oh, what if we had a level curve that was this elliptical thing, right? Tilted elliptical thing, equal to k, I said. And we found its partial derivatives, and guess what we found its partial derivatives to be? OMG. And of course, the derivative of the constant was 0. Whoa, whoa, right? Pretty cool. So again, I did 2 examples where one, I told you it was exact from the beginning, so you didn't have to verify, and then one where I didn't tell you it was exact, right? But in reality, if you went back to the original slide, we already knew what our answer was going to be. And then I gave you some practice on just here's 4 equations, check to see if any of them are exact. All right, and in our live session, so this is the first differential equation, really, right? On that first slide, exact differential equation. Then I did number 1 from the 4 equations that I said check to see if it's exact. We solved that one in example 1. And then on those 4 of those 4 examples, there was only one other that we showed to be exact. We'll do that problem in our live session, and I will see you then.